The modern automotive industry has a weight problem. To increase fuel efficiency and extend driving range, manufacturers are stripping out conventional steel and replacing it with lightweight multi-material architectures, specifically mating aluminum 5052 with ultra-high-strength steel. Fusing these two metals together using conventional welding is practically impossible. The differences in their physical and chemical properties result in the formation of brittle intermetallic compounds at the weld line, compromising the joint's integrity. The standard industrial alternative is self-piercing riveting, or SPR. It is a purely mechanical process that punches a steel fastener directly through overlapping sheets, creating a robust physical lock without melting the base materials. For softer alloys, it works effectively, but the current generation of hot press forming steel reaches a tensile strength of 2 gigapascals. At this level, the steel sheet is harder than the fasteners designed to pierce it. Attempting to drive a rivet into 2.0 gigapascal steel results in immediate physical failure. The standard C-type rivet buckles upon impact, while the heavy-duty HD2 rivet fractures inside the die cavity. To force a physical fastener through material this dense, we have to lower the steel's yield strength exactly where the rivet will strike. The solution is laser-assisted local softening. Seconds before the mechanical press activates, a continuous wave laser traces a precise 5 mm ring on the top steel sheet. This heat softens the target zone, allowing the rivet to penetrate into the aluminum layer below. Achieving an 8 kN joint requires more than raw heat. It requires finding the exact thermal balance where the steel yields without losing its structural integrity. To find that balance, we must deconstruct the joint from the macro level down to the microstructure. To understand why certain joints hold while others fail, we begin at the macro scale with the defining physical metric of a self-piercing rivet. That metric is the interlock width, the horizontal distance from the deformed rivet tip into the aluminum sheet. While the seals prevent environmental intrusion, the interlock is the primary load-bearing anchor. It's the physical hook holding the bottom sheet under stress. Testing dozens of variations in laser power and scan passes reveals a clear divide between joints that hold and those that tear. In this cross-section matrix, thermal input clearly dictates rivet deformation. At 100 watts, the steel remains too stiff, forcing the rivet straight down with zero outward flare. But applying 200 watts over 3 to 5 passes produces an expansive mechanical interlock. This scatter plot maps tensile strength against interlock width. There's a strong correlation. As the flare widens, shear capacity climbs. An interlock width of 0.2 millimeters is the threshold for success. Below this, joints fail early. Above it, shear load stabilizes. Generating an 8 kilonewton shear load is impossible without forcing that 0.2 millimeter interlock flare. The question is, what internal material condition allows 2.0 gigapascal steel to bend rather than shatter? Making the 2.0 gigapascal steel yield to the rivet requires carving out a localized zone of reduced yield strength. We track this by measuring the Vickers hardness across the cross-section of the laser-treated zone. This graph charts the hardness profile moving across the irradiated path. The untreated steel sits at a baseline hardness of 633 HV. The green line representing 100 watts of laser power remains flat, showing no change in the material. At 100 watts, the heat input is insufficient to trigger microstructural recrystallization. The steel remains at 2.0 gigapascals, causing the rivets to fail. Increasing thermal input to 200 watts over 3 passes reconfigures structural resistance. The profile shows a deep U-shaped basin, dropping to 346 HV. Comparing successful tests reveals a strict limit. The target zone must drop below 420 HV to prevent rivet fracture. This thermal basin provides the mechanical compliance needed for the rivet to penetrate and flare out into the required 0.2 millimeter interlock. These results take a counterintuitive turn at higher power levels. If 200 watts softens the steel, the assumption is 300 watts softens it further. Instead, at 300 watts, the tensile strength drops back to 4.79 kilonewtons. The hardness data explains why. Looking at the orange line, the profile creates a W shape. In the center of the irradiated zone, the hardness rises sharply back to 500 HV. This occurs because the 300-watt laser pushes the steel past its austenization temperature. The extreme localized heat causes a rapid thermal shock. When the laser moves on, the surface cools so quickly that it locks the crystal structure into fresh, brittle martensite, re-hardening the target zone. We can contrast this with the phase evolution inside the optimal 200-watt joint. The untreated base metal consists of pure, fine martensite, dense and inflexible. At point C, the center of the 200-watt joint, the microstructure is mixed, featuring a coarser grain structure. Moderate heating at 200 watts creates a slower cooling rate, dominated by internal conduction. This allows the hard martensite to transform into a mixed phase containing nearly 49% bainite, a much softer microstructure. The perfect joint isn't achieved by maximizing heat, but by carefully controlling the cooling rate to foster soft bainite and avoid brittle fresh martensite. We can synthesize these constraints into a single operational process map. Dark blue zones indicate insufficient heat. Orange and purple blocks represent microstructural rehardening and fracture. The optimal parameters exist in this green zone, from 200 to 250 watts across 2 to 4 passes. On an automotive assembly line, operating within this specific zone significantly reduces total energy consumption. Traditional resistance spot welding requires 10 to 15 kilojoules of electrical energy per weld. This localized laser softening process achieves an 8 kilonewton hold using a mere 1 to 6 kilojoules. By reverse engineering these phase transformations, we have established a high-strength, low-energy method for joining ultra-high-strength steel and aluminum, securing the structural foundation for future lightweight vehicles.